Welcome to section 4.3 in linear algebra. I want you to keep in mind throughout all of these videos that if I'm talking too fast or too slow, if you go to settings, you can adjust the playback speed to go slower or faster. All right, today we're going to talk about the definition of basis and how to find a basis for null A and call A. Last time we talked about the linear independence definition, and it's no different than the linear independence definition we've had all semester. So, a basis is a set of vectors in a vector space that both spans the vector space and is linearly independent. Those two things have to be true. The standard basis for some familiar vector spaces are as follows. For Pn, which is the set of polynomials of degree less than or equal to n, the standard basis is 1t squared up to t to the n. Notice that that's n plus 1 vectors, which will be important when we talk about dimension. For M22, it's the four matrices that have a 1 in one spot and zeros everywhere else. And that's got 2 times 2 equal 4 vectors. And for Rn, we've got E1 through En, that's n vectors. For example, in R2, the standard basis would be 1, 0 and 0, 1. All right. Let's find a basis for the set of vectors in the plane x1 minus x2 plus x3 equals 0. So we've got a single equation here, and what we want is we want a basis for null A, where A is the coefficient matrix, 1, negative 1, 1. So, in order to do that, we have to reduce A augmented with 0. Now, there's no reduction to do. 1, negative 1, 1, colon 0. It's already reduced, so we've got three variables. x3 is free because there's no pivot in the third column. x2 is free. And x1 is positive s minus t. So solutions look like s times 1, 1, 0 plus t times negative 1, 0, 1. So the basis is spanned by the two vectors you see there. Basis for null A is 1, 1, 0, negative 1, 0, 1. It's a basis because it spans, and last time we saw that this process of finding a spanning set for null A will always give you a linearly independent set. So we've got two vectors, they span null A, and they're linearly independent, so they form a basis. Okay, spanning set theorem. Suppose we've got a set of vectors in a vector space, and we take the span of those vectors. So H is the span of V1 through Vp. What this theorem says is that if one of those vectors is a linear combination of the others, you can toss it out and you're still going to span the same set. So if V1 is a linear combination of V2 through Vp, you can toss out V1 and you'll still get H. You can keep tossing out vectors until you have a set that is linearly independent, and that will form a basis for H. So a basis is the smallest set that will span. Anything smaller wouldn't span the whole space. And the largest set that's linearly independent. All right, so let's do some examples here. here we're working in P1, which is the set of polynomials of degree less than or equal to 1. By inspection, write one of the vectors as a linear combination of the others. Well, if I add P1 to P2, looks like I'll get P3. Because 1 plus 1 is 2, and 8t plus negative 8t is 0, so that's true. So P3 is not needed in terms of spanning the set. If we let H be the set span P1, P2, P3, then P3 is extra. So we could take as our basis P1 and P2. Now, how do I know they're linearly independent? Well, P1 is 1 plus 8t, P2 is 1 minus 8t. One of those polynomials is not a linear combination, a multiple of the other, so they're linearly independent. Okay, next section, pivot review, because we're going to be working with pivots a lot here. The columns of matrix A are linearly independent if and only if AX equals 0 has only the trivial solution. So, pause the video, A has a pivot in every blank, and then try and fill in the next blank too. All right, A has a pivot in every column, because you don't want any free variables. AX equals B is consistent for all B if A has a pivot in every row, because then you won't get a row that is all zeros and then a B at the end when you augment with it, when you augment A. All right, so let A be the matrix whose columns are the given vectors. Do the vectors span R3? Are they linearly independent? Do they form a basis? To answer that question, we're going to look at pivots. We're going to put those vectors into a matrix, reduce the matrix, which I did, put those vectors in here, and then I reduced. I didn't go to reduced echelon. I only have to go to echelon because I'm looking only for pivots. So, do those vectors span R3? Do we have a pivot in every row? Yes, we do. Are those vectors linearly independent? Do we have a pivot in every column? No, we don't. So do those vectors form a basis? No, they only satisfy one of the requirements. To form a basis, you have to span and be linearly independent. Okay. How to find a basis for null A and col A. And you need to know this. And pretty soon we'll add how to find a basis for row A once we start talking about row A. So finding a basis for null A is pretty easy. Solve AX equals 0 and the spanning vectors form a basis. So we did that, for example, in this first example here. We found a basis for null A where A was this matrix. So that's pretty straightforward. And then finding a basis for col A, reduce A to echelon form, and then don't use the pivot columns of B. Look at the pivot columns of B and use the corresponding columns of A. All right? And the reason you can't use the columns from B is that row operations will actually change the column space. So here we go. Assume A is row equivalent to B. Find a basis for null A and col A. All right, so A has already been reduced to B. To find a basis for, let's do the easy one first, col A. To find a basis for col A, we look at the pivot columns of B. Columns 1, 3, and 5. That means we want to use for our basis columns 1, 3, and 5 of the matrix A. So basis for col A is 1, 2, 1, 3, -5, -5, 0, -5, and, can't read, -3, 2, 5, -2. Again, you have to go back and use the original columns from A, not from B. All right, for a basis for null A, we can just use B augmented with 0, and that's the matrix 1, 0, 0, 0. Or you can do this, you can augment it in your head. You don't actually have to write down that extra 0 column. I'm okay with you just doing that in your head. But since this is a online class right now and you can't ask a question right away, I'd rather err on the side of being too thorough than not thorough enough. All right, so there's 1, 2, 3, 4, 5 variables. So we're going to start at the bottom with x5. X5, this equation right here says x5 is 0. X4 is free because the fourth column is not a pivot column. So x4, I'll call it t. X3, reading this equation here, x3 is 7/5 t. X2 is free, I'll call it s. And finally, x1 is -2s minus 4t. So we're going to have two vectors in our basis. One will be the vector corresponding to the s's, and one will be the vector corresponding to the t's. So a basis for null A is, okay, our s vector, I'm going to pick off the coefficients of s. -2, 1, 0, 0, 0. And then the t's, -4, 0, 7/5, 1, 0. All right. One thing I want to point out is don't be lazy and just say, leave off basis for. Because if you just say null A is that's not true. What I have there is just a set with two vectors. A set with two vectors can't possibly make up all of null A. So you need the word, the two words, basis for null A is that set. All right, this is going well. I kind of wish you were here though. I'm a little lonely. True false time. So I suggest you pause the video, do these, and then come back and hear the answers. All right, so here are the answers. A linearly independent set in a subspace H forms a basis for H. False. Needs to span 2. If a finite set of non-zero vectors spans a vector space, then some subset forms a vector space of V. This is true. This is part of the spanning set theorem. Spanning set theorem says you can keep tossing out vectors that are linearly dependent until you get a lean mean fighting machine. A basis is a linearly independent set that is as large as possible. That's true. If you added one more vector, you'd have a dependent set. A basis is a spanning set that is as large as possible. That's false. You want it to be as small as possible. The columns of an invertible n by n matrix form a basis for Rn. That's true, and that's because by the invertible matrix theorem, the columns of an invertible matrix span Rn and they're linearly independent. So you have those two conditions met. If B is an echelon form matrix of A, the pivot columns of B form a basis for col A. False. You have to go back and use the columns from A. A single vector is linearly independent. Well, that's a trick. It's false because that single vector could be the zero vector. So you'd have to say a single non-zero vector is linearly independent. Then it would be true. All right? And then finally, if H is the span of V1 through Vp, then V1 through Vp is a basis for H. Again, false, because no one told you that V1 through Vp is linearly independent. So you would need linearly independent also. All right, so here are some practice problems, 3 of them. And you can go through and do those without looking at the answers. And then on the last page, I've got solutions written out. And I did that sort of to save video time. And you can read those solutions on your own. And then if you have questions during one of our Zoom sessions, you can ask me about that. All right, that's all right.